Yeah.
You go ahead.
Yes. So what I was saying is, okay, that going towards the quantum error correction, the first step is going towards the similarly as we were doing in the classical repetition code, that instead of storing information in the physical qubit, the information will be in the copied or will be stored in the many physical qubits, and that physical qubit compromise, we call it the one logical qubit. So by dividing the information, we just make sure that that noise will not, if there is a noise, that it doesn't affect the information in the system, and it can affect the very smaller part of the code, and that we can detect by using a different kind of codes we have. That so one of which is the surface code. So here they started with the discussion about that. Okay, that what are the conditions on which this kind of logical errors can be decreased. So what are the conditions need to be considered, that so that we get the minimum logical errors in the system. So here, so equation one is from where it started. So they here shows that, okay, that how the logical error could be depend on the error in the each qubit in the system. So here epsilon d in equation one is the logical error, and P is the error for each physical qubit. Is the probability of error in the physical qubit, and PTH is the threshold probability, that below which, so threshold probability is the minimum probability above below which there is sorry, let me check. So it's a minimum error above below which there is that noise could not affect the qubit. So it will give the threshold probability of the system. So D is it's called important parameter here, which is called the core distance. So D is actually so it will tell you, okay, how minimum number of changes in some code is required to change the output of a logical qubit in the system. So for example, like if I in the classical system, so in I can write something.
We can see your
Hello.
screen, but we don't see your writing. We see the paper.
Okay. Uh-huh. Just a second. Okay. Silent D, which is directly proportional to P by PTH, and it's a D plus 1 by 2. So, so this is what I say is a logical error. So this is what I say is a physical, sorry, the probability of, both are the probabilities, the probability of error in physical qubit. So, and this is a threshold probability of the error. And what is D? And D is a very important parameter here, which we're going to change in the system. So what is D is, as I say, is the minimum number of bits required to change the output uh, of a logical qubit. So what I am saying is that, so if I have now in terms of a classical things, I will think about a bit, otherwise I will think about a qubit. But most of the message will remain same, that if I have a bit which I am going to transfer 000, so if I'm going to transfer 0 to 1, so let's see, there is an error and it transfers to 1. So what I can do is I can transfer 000 instead of 1, I will send a 3 copies. So now if a source will get 001, then they know that the information which is sent is 0, because the probability of getting 0 is larger as compared to 1. But now if the system want to, if the logical error, what I say is that if the somebody is not getting 001, but 1 1 1. This means that if there is a flips in the operator like 3 times, then we'll get the logical output, which is 1. So this means that the minimum 3-bit flips are required to change the output information of the system, that the logical qubit will not give anyway now 1. So therefore, D will be 3 in this case. So in this way that we will going to see the similar way that minimum number of qubit need to change the information in the system or get an error so that the output logical output should be changed. So this will be the D values we will say. Okay. So in terms of surface code, this also represent that the edge to edge distance, that is the shortest edge distance between the two qubits in the system. So here, that's why in the figure, you can, when they are saying about you can consider 3, 5, 7, then you are going to change about the information how that with the increase of D, this logical error could be decreased. So what we know is it's a probability, so it's less than 1 always. So if we are able to achieve in the limit when the P threshold is much greater than P, in this limit, we can say that, okay, if this limit is achieved, then with the increase of D, this logical level will be decreased. So this will be the basic principle on which this whole code should work, that, okay, that I should make the circuit in such a way, that hardware such a way that the threshold value should be more than the probability of P. And if I now increase the D values by 2 factor or something, then this should be decreased. The logical error should be decreased. So this will be the epsilon D, which we will compare and see that, okay, how it will changes as I am going towards the higher values of D. So then they also introduce a parameter lambda, which is basically if I add two sides or two qubits to the D system or increase the D by 2 and then the ratio, so this should be equal to lambda. So this will be the parameter of suppression of error. So if lambda is large, we see that, okay, more and more better is our hardware is, and we have suppressed the error in the system lambda of the system. So this is what the equation 1 was saying. So, and the all parameter it have. So basically these are the all parameters which we will see in the next section, that how they are going to study these things. Okay. So this is the lambda D, as I am saying. So it will be depend on it's just a fitting parameter which will just tell you, okay, that the error suppression, it's called error suppression factor, that how well your code. So after that, they just want to tell that, okay, what they are doing in this work, that, okay, they use a 72 qubit processor to and the surface code and also using a 105 qubit processor. So they are using 105 qubit processor as a total, and then the 70 2 qubit processor is used here to arranged as a decoder in the distance 5 and distance 7. They are using a bigger model in the system. So here there are two arrangements which we will see. That is 3, 5, and 7. I think they have a previous paper. They have already studied 3 and 5 qubits distance, where that they, and now they want to introduce that if they increase the distance by 2, which is by 7, that how well they can achieve the quantum error and how well the suppression is achieved in this system. So this is what their model is. So this is the surface code. Uh, so yeah, so yes. So this is the code that they represent, and here these are the data qubits with the orange color, which represent the qubits where the data is stored, or where the bits are stored, and then they represent the measurement qubit with the different color here, blue, which measures the information of these 4 qubits, and that how, and then there is also they introduce the leak removal qubit, which will also call, which will be I think they did not mention these qubits always. In some simulation they include it. Okay, that we remove the leakage and the strain interaction or from the qubit and study the effect of the 3, 5, and 7 on this whole picture, the system. So here they considered that, okay, they considered three, D3 to D5 and D7, which is represented by a red boundary, orange boundary, and the black boundary here. So in D3, so as they also introduced that if you want to uh, make a error code which is able to calculate the error up to 3 codes, then you need a 2d square minus one number of qubit to be introduced. Therefore, for 3, they already consider that these many qubits, that there are 9 qubits, which data qubit, 9 data qubit, and then there are 1, 2, I think 4 measurement qubits are used to study the system. Then they firstly here in equation figure 2, they consider the error probability distribution for the individual qubit for 105 chip they were doing. So, and they want to here show that, okay, that if they have a 1 qubit only, that single physical qubit has a very have a probability which is 1/1000, which is very small. And similarly for the black, they control that how well it is worked independently, and then they also want to tell the measurement probability, and I think this one is deterministic. So, yes, so it's a weight detection probability of distance 7. So, this is what they have done. So what they have done further is that they have used some neural network approach to calculate this the sorry, what I have done. So what they use is that now for distance 7 surface coder, they used 49 data qubits and 48 measure qubits and 4 additional equal qubit to improve that data from that. So what they here show is their previous calculation for D3, which is and D5. Then they show that, okay, how well they have improved by using their neural network approach. They are going to calculate it up to 250 cycles of a quantum error correction. So this is the so many cycles they have used, and these are the median values they have calculated. And it is shown that if I go from 5 to 7 number of uh, uh, code length, sorry, 5 to 7 code length, then the error is logical error probability is decreased by a factor of, I guess, zero point 0.2 something. So this is what they have showing here, that if there is a 3 qubit, that their code length is 3 only, then it is quite large, which is around 0.5, and then it is decreased by the factor of 2 in this calculation. So then they fit the parameters here and try to extract the separation length in the system. So this is what they are calculating here, that separation length with the change of d, that how they are how they are calculating. So this is the logical error per cycle as a function of surface core distance. So as they are increasing the 3 to 7 number of code distance, then they see that this lambda is quite large, which is 2.14 they got from is they are comparing 3 and 5, they get 2.14, and then 5 and 7 it's 2.12, and the average is 2.14 around. So which shows that they got a larger value of error suppression parameter. That's what their lambda is. So they also mention about the parameters that the time that the T1 is 68 microsecond and 6 and T2 is 89 microseconds. So I was not very much sure about the methods they were using, because yeah, so it's like, so I know that this one is they were mentioning the simulation in the small thing here, that okay, this is for the three different value of D's. They were calculating the simulation results by calculating these similar parameters. But now they also include here, they were saying that the strain interaction and the leakage of the qubits also they introduce and calculate that how well it is going towards the zero. So I think in this limit, in this section, they were discussed more about that. Okay, that if they are going to be in that threshold value, below that threshold value, they indeed are getting the values which are quite high in this. And so I still not know about that. Okay, how I can we can understand the scaling of there, because what I understood, as much as I know about the surface code, that okay, if I am attaching more and more number of this physical qubits in the system, then there are there are many parameters to control as well, which they are, I think, try to achieve by changing the neural network. They were mentioning about that. Okay, they are considering, I think, 250 cycles of the neural network to study that kind of information they were having here. So this is about this section actually whole. I think so. I covered most of the things. Yeah. So there is one more. This is what they have told, that okay, that's what they are got, that okay, their logical qubit lifetime is 291 microsecond, which is much greater than the physical qubit lifetime, which is 85 microsecond. So this means that their logical qubit can sustain more information about the data stored in the physical qubit for the longer time. The information what they are sharing, that is, I think, I can understand that okay, that if I have now more length of the parameters and all, so then I can easily change the qubit, that okay, if there is an error, I can change that qubit particularly, and all over it doesn't affect the other qubits, and I can get a better result as the information. So yeah, so I think that's what the major result of this section.